Hello students, welcome to the 27th lecture on particle physics, and we have started discussing neutrinos. And what I had told you that neutrinos are the most abundant particle after photons, but they are least understood. And it was proposed by Wolfgang Pauli in order to save energy momentum and angular momentum conservation laws. While he proposed this particle by sending a letter to the participants of a conference which was held in Tübingen, Germany. And he wrote in that I am proposing a neutral spin half particle, called it neutron. Later, Fermi took his idea and framed theory of beta decay, which today we know by the name Fermi's theory of beta decay, in which neutrino is an important ingredient. After that, search for the neutrinos started, and in 1956, Rines and Cowan at Savannah Nuclear Reactor Power Plant discovered neutrinos. Rather, it was anti-neutrino, because we will see that at nuclear reactors you can have only anti-neutrinos. Now let's start with this concept that this was proposed by Pauli, and in that letter he mentioned that it is almost impossible to detect this particle. And that is why the theorists in that audience were not very hopeful of having such type of particle. And he even told to one of his friends that I have done something very bad today by proposing a particle that cannot be detected. It is something that no theory should ever do. Pauli did not publish this idea until 1934, as he thought it to be too speculative. Now, when Fermi gave his theory of beta decay in 1933, he rechristened this neutron of Pauli to neutrino. Fermi gave his celebrated theory of weak interactions in analogy with quantum electrodynamics, the theory that deals with the quantum theory that deals with the interaction of charged particles with the photon field. And that is a very well accepted theory, and that time also it was accepted. And here what he proposed in the case of quantum electrodynamics, the theory of electromagnetic interaction, photon is the mediating quanta. But since at that time when Fermi was framing this theory, there was no mediating quanta, he gave 4-point Fermi interaction. That is why in this Feynman diagram, you will see that the interaction is happening at a point without the help of the mediating quanta, and a neutron is getting converted into a proton, electron, or antineutrino, or a proton is getting converted into a neutron, positron, and neutrino. And he wrote the matrix element keeping this interaction strength to be GF, psi p bar, an outgoing proton, gamma mu, telling us the vector nature of the interaction in analogy with QED's interaction, which is described by a vector interaction because photons are vector particles, psi n, psi e bar, gamma mu, psi nu. Now later we will see that with this vector interaction gamma mu, it is not able to explain the experimental data, as well as without propagator it will not be, the cross sections will not be able to saturate. If you use this transition matrix element and obtain the expression for the scattering cross section, what you will obtain for neutrino electron scattering, for example, a straight line. And that means there will be divergence. This is the center of mass energy. This is the cross section. You will obtain a straight line. But the experimental observation showed that the cross section increases and then saturates. The other reason for the cross section to saturate is that had it been increasing all the time, then that means for higher energy neutrinos, the probability of interaction will be more, and therefore if the neutrinos are of very high energy, we should be able to see them very frequently, but that never happens. Therefore this formalism was later modified, which we know in the weak interaction theory as V minus A theory, that consists of vector and axial vector, but that is a topic that will be discussed in a separate unit. Now let us come to the discovery of neutrino. What I had told you in the last class, that it is really difficult to detect a neutrino, and that is why after the theoretical proposal it took more than 25 years to detect this particle. And what was first, this was a thought experiment. The thought was, if really neutrinos are coming, then if we have a target material like proton, then this interaction will produce positron and neutron. Now, if we are talking about detector material, then we know that detector materials are made up of atoms, and atoms are nothing but matter, and that means we are talking about electron, proton and neutron in the detector. Therefore, this positron, which is an antiparticle, this will immediately annihilate in the presence of the electron, and you will have two photons back to back. Therefore, one photon will go in this direction and another photon will go in this direction. Therefore, instantly you will have the annihilation of positron into two photons, and then the neutron which will move, cadmium chloride was present, and because of cadmium, as we have in the nuclear power plants cadmium rods to absorb neutrons, and that is what we call as the controlled fission reaction, because if we don't place such thing, then it becomes an atom bomb. The difference between an atom bomb and here is that in the case of nuclear power plants, we have control rods, and these control rods are the cadmium rods, and they are good neutron absorbers. Therefore, cadmium was placed inside this detector and to absorb neutron. And what was the thought? The thought was, when cadmium will be absorbed by this neutron, then a photon will again be emitted. Therefore, two instant photon and one delayed photon would be the signature that a neutrino has interacted with the proton. This was the thought behind the Rhines and Kovans experiment. Therefore, what they did, they used 400-liter mixture of water and cadmium chloride. And the reaction that they thought that an antineutrino will interact with the proton target available from the water, as water has oxygen and hydrogen atoms, and then we have neutron and positron, and this positron will immediately annihilate with an electron of the surrounding material in the detector, giving two simultaneous photons, and the neutron slows down until it is eventually captured by the cadmium nucleus, resulting in the emission of photons some 15 seconds after those of positron annihilation. Therefore, this is the picture which demonstrates that this red is, say, a neutrino which is coming and hitting the target material, producing a positron, and then positron is getting annihilated with the electron in water, and then two photons are instantly emitted in the backward direction, and then the neutron recoils and the neutron gets absorbed by the cadmium atom, and then we have a delayed photon after a few microseconds. Therefore, two instant photon and one delayed photon was the signature that really a neutrino has come. Now there are various sources of neutrinos in the visible universe, and these sources don't have unique neutrino energies for all of them. We have solar neutrinos, we have atmospheric neutrinos, we have relic neutrinos, we have reactor neutrinos, we have geoneutrinos, and all that. And they have different neutrino energy spectra. And in this picture, I am showing you the various neutrino sources which are giving rise to neutrino spectra, which really have got different nature. For example, the cosmic neutrino burst, Big Bang nucleosynthesis, the solar neutrinos, geoneutrinos, reactor antineutrinos, atmospheric neutrinos, very high energy neutrinos. Then we will talk about cosmogenic neutrinos. These are the various sources of neutrinos which are carrying energies in the different region. And as you can see that the neutrino energy is varying from a micro electron volt to more than extra electron volt. Therefore, we have trillion volt electron volt energy of the neutrinos, we have million electron volts energy of the neutrinos, we have kilo electron volts energy of the neutrinos, and so on. Therefore, neutrinos are coming from different sources. They are having different energy spectrum, and we have in nature very high energy neutrinos, and that is what we are talking about, more than 10 power 18 electron volts of neutrinos. And therefore, it is important to understand these sources. And let me start with a very well-known source of neutrinos, and that is solar neutrinos. As I had discussed in the last class, that sun, inside the core of the sun, nuclear fusion reaction is going on, and basically proton burning is going on, and that proton burning is giving rise to neutrinos. And the basic reaction that is happening inside the sun is that proton is burning to give you a deuteron plus positron plus neutrino plus energy. And then we have similarly another 1d2 coming from the two protons, and then these two combine to finally give us 4 protons are burning to give us a helium nucleus plus 2 positrons plus 2 neutrinos plus energy. And these positrons, since inside the sun we have again the matter dominance, and therefore immediately they annihilate to give us more energy, and they annihilate with electrons to give us more energy. While these neutrinos, they immediately come out. As we know that from the sun, light takes about 8 minutes to reach us, while these neutrinos, if we talk about them, then we will see that they don't have any weak interactions, and therefore they come out instantly, while the photons which are produced inside the core of the sun, they takes millions and millions of years to come out to the surface of the sun because of multiple interaction, as photons are the particles which are quanta of electromagnetic interaction, and this we will discuss later in this lecture. Then we have atmospheric neutrinos, reactor antineutrinos, geoneutrinos, relic neutrinos, supernova neutrinos, and all the others like cosmogenic and the others. But these are the important sources of neutrinos. Their fluxes are really large, and we shall talk about them in greater detail. Now, this is the picture of the photosphere, the sun, the surface of the sun, which we see every day. As we know that sun has, besides the core, three important layers: photosphere, chromosphere, and corona. This corona almost extends to the earth, but photosphere, what we see every day. During eclipses, we see the corona part, but here we are talking about the reaction which is going on inside the core of the sun. Therefore, we have the core where nuclear fusion reaction is going on, and then we have the temperature of the core is about 10 power 7 degrees Celsius. Then we have photosphere, the average temperature of the surface of the sun, which we see every day, that is around 6000 degrees Celsius. Then we have chromosphere, chrome means color, and this temperature varies from 4000 degrees Celsius to almost 10,000 degrees Celsius. And then we have corona, whose temperature almost extends to million degree Celsius. But since the density of the particle is very, very small, therefore we are unable to feel the presence of this much of temperature carried by a particle. And therefore, what is important is that the inside the core, proton-proton bonding is taking place, where the temperature is 10 power 7 degree Celsius. And the most important thing is, we believe in Becquerel's model, John Becquerel's model, which says that what exactly happening inside the sun. And it is his and his group's prediction for the neutrinos and other properties associated with the parameters in the model, which is known by the name standard solar model. Therefore, whatever we are talking about is within the context of that standard solar model of Becquerel. Therefore, what we are talking about, that basic reaction we can summarize as 4 protons are burning to give us alpha particle, that means helium nucleus, positrons, neutrinos, and this much amount of energy. And then these positrons, immediately they annihilate with the electrons, and we have extra 2.04 MeV of energy, as the masses of electron and positron, 2 for them is 1.02, and since there are 2 positrons, 2 electrons, therefore that is giving rise to 2.04 MeV of energy. So therefore, this is not a one-step process. 2 protons here and 2 protons here, they are burning to give us deuterons, and then deuterons are combining to give us helium-3, and then helium-3 are combining to finally give us an alpha particle. Therefore, this is how nuclear fusion reaction is taking place inside the core of the sun. Now the question arises, why there is a release of energy when protons are burning? And the answer to that is simple. As from class 12th we know that if we plot atomic number on the x-axis and the binding energy per nucleon on the y-axis, then initially the binding energy increases, and then there is a peak at one of the isotope of iron, and then there is a saturation, and this peak is around isotope of iron is around 8.8 MeV, and then there is a saturation. Instead of talking about binding energy, here I have talked about the mass per nucleon, and that will also tell you that why the energy is released in fission and fusion, and this will also convince you why cannot we have fusion of uranium nucleus, or why cannot we have fission of oxygen nucleus or carbon nucleus, etc. Therefore, here mind it, I am plotting mass per nucleon on the y-axis and the atomic number on the x-axis, and this, just look at this picture of binding energy per nucleon, invert it, take the mirror image of this. What you will realize that when we are talking about proton and the protons are combining to give us deuterium nucleus, deuterium to tritium to alpha particle to heavy nucleus, mass per nucleon inside the nucleus is decreasing. And this is what I am showing it by these two diagrams. These are the weighing scales, and what I have done on the left hand side, we have 2 protons and 2 neutrons, those are independent. And then in the left scale of this left diagram, we have helium nucleus, which also consists of 2 protons and 2 neutrons. And you can see that the independent protons neutrons mass are more than the mass when they are in the helium nucleus. And this difference in mass comes out in the form of energy. This happens up to the isotope of iron nucleus. Similarly, if we talk about uranium nucleus and we break it into lighter nucleus, that is known by the name fission, then in this case you can see that uranium mass, the nucleons inside the uranium nucleus, they are heavier than when they break into lighter nuclei. And that means mass per nucleon in the lighter nuclei are smaller than in uranium or in thorium or nuclei which we fission to get energy. And that means mass per nucleon is least in the case of the isotope of iron, which we say that has got maximum binding energy. And that is why if you look at the curve which is before the isotope of this iron nucleus, we can have fusion of iron nuclei, lighter nuclei to give us a heavier nuclei. We can have fusion of helium to get carbon, to then we can have calcium and all that up to the isotope of iron, and we will get energy. But here when we reach to iron, then we cannot have either fusion or fission, because we will go in the above scale of this mass per nucleon, and that means we will violate law of conservation of energy. We have less energy, and then we want to talk about more energy on both these sides. And that is the reason if you talk about a barium nucleus or krypton nucleus here, you cannot have fusion of krypton nucleus, because that will give you a heavier nuclei, and then heavier nucleus will have more mass per nucleon, and that will be violation of the conservation of energy. And this is the reason why you have, when you talk about proton burning to get a helium nucleus, you have 4 nucleon. They are combining to give you a helium nucleus, but the mass per nucleon inside the helium nucleus is much smaller than the mass of the independent nucleons. And this difference in mass comes out in the form of energy. That is why this fusion reaction is taking place, and you are getting energy inside the core of the sun. Now 4 protons fuse to produce a helium nucleus. This is what we are discussing. The mass difference of 0.044 into 10 power minus 27 kilogram is converted into energy. And this is what we are talking about, a release of energy of around 24.73 MeV when 4 protons are burning. Now, it has been measured that the luminosity of the sun is around 24 into 10 power 38 MeV, which is equivalent to, I am talking about an experimental measurement, which is equivalent to 10 power 38 nuclear reactions which are taking place per second. Or equivalently, we can say that 4 into 10 power 38 protons which are burning per second. Therefore, mind it, to have this luminosity which we observe every day from the sun, to have this much of energy coming to us, what's happening? 4 into 10 power 38 protons are burning per second. Now, mass of the sun is 10 power 30 kilogram. Number of protons in the sun, that means you multiply it by the Avogadro number, and this will turn out to be around 10 power 57. That means the total number of protons inside the sun is 10 power 57. And then if per second 10 power 38 protons are getting consumed, then how long will it take to consume 10 power 57 protons, and that will be the lifetime of the sun. And this is the lifetime, what we call it as 9 billion years, where 4.5 billion years have already been spent and another 4.5 billion years to go. Therefore, just it is a naive approach to see the lifetime of the sun. This is the total number of protons in the sun, which is 10 power 57, keeping in mind that the mass of the sun is 10 power 30 kilograms, and since there are 10 power 38 protons are burning per second, therefore the total time that will come out to be roughly around 10 power 19 seconds. And that 10 power 19 second, since we know that the 24 hours is 86,400 seconds, from here that is 1 day, and then you have 365 days for 1 year, you can calculate that this will turn out to be roughly 9 into 10 power 9 years. Okay. Now there is an interesting topic, and that is very important to understand. We are talking about the core of the sun has got a temperature of 10 power 7 degree Kelvin, and we cannot play with it. It is there in the standard model, and we cannot vary the parameter. There is not much independence in the parameters of the standard solar model. This model is so beautiful, so acceptable to the scientific community. We believe that the temperature of this core of the sun is 10 power 7 degree Kelvin. Now let us talk about an interesting thing. When we are talking about the two protons which are burning, that means these two protons have to come together to get fused. But we know that these protons are positively charged particles, and therefore there will be Coulomb repulsion between these two. And when there will be Coulomb repulsion, first we have to overcome that Coulomb repulsion, then only they are going to get fused. Now, how much temperature is required to overcome that Coulomb repulsion? This is what I have shown here. This is 3 by 2 kT is 1 by 4 pi epsilon naught Q1 Q2 by R, the Coulomb energy. And just I am putting here the charges of proton, 1.6 into 10 minus 19 Coulomb. And this R is the proton size, that is roughly of the order of 1 Fermi, or you say 10 power minus 15 meters. When you calculate it, K is the Boltzmann constant. When you calculate it, this will turn out to be 10 billion Kelvin. Therefore, you see the Coulomb barrier is very high, 10 billion Kelvin. That means almost 10 power 10 Kelvin. While the core's temperature is 10 power, slightly more than 10 power 7 degree Kelvin. And this means that if we have a barrier of 10 power 10 Kelvin, then how come these two protons are able to fuse? We understand it quantum mechanically. Classically, it is impossible to understand. Quantum mechanics tells us that there exists a concept of quantum mechanical tunneling. And to describe it pictorially, we say that we have a barrier of height, say 10 meters, and we want this car to cross this barrier. Then you know that it is impossible to cross this barrier, to jump this barrier. While if we reduce the height of the barrier and we have umpteen numbers of cars which are trying to cross this barrier, then there exists a chance that this car, one of them, would be able to cross this barrier. While if we further reduce this barrier to a height of say 10 centimeter or 20 centimeters, then more cars will be able to cross this barrier. Therefore, the important point is that either we have umpteen numbers of cars which are trying to cross the middle barrier, okay, which has got a height of say 1 meter or 2 meters and one will be able to jump. Here, when we are reducing the height of the barrier, then many of them will be able to cross. Therefore, the point is, if we are talking about the temperature of 10 power 9 degree Kelvin inside the core of the sun, while requirement is 10 power 10 Kelvin, then many of them will be able to cross. But here, the barrier is 10 power 10 Kelvin, while core temperature is 10 power. Therefore, this is 10 power 10 Kelvin and core temperature is 10 power 7 Kelvin. Now, instead of that, let us talk about another concept. We have an infinite well, a well of infinite depth, quantum mechanical well, you know. And if we, for example, take a classical picture, we are putting a frog and say the depth of the well is 20 meters. Then we know that the frog will never be able to come out of the well. Now we reduce the height of the well. Say we are talking about a big bucket of water, and then there are many frogs inside that well. Then if many of them will try, then there exists a chance that one of these frogs will be able to come out. Or if we have got only one frog, then also if it tries many times, several times, then there exists a chance that once it will be able to come out of the well. The same happens here also, that though there are 10 power 57 protons inside the core of the sun and only 10 power 38 protons have to fuse per second. Try to understand this by looking at the concept where we have $1 million, for example, and this fellow on the left has donated $1,000 to some charity organization. Then if I ask you the question that subtract 1,000 from million, then you will say that this will for sure not be equal to 10 power 3. Rather, it will be a number which will be again very close to a million. The same concept is here. Though 10 power 38 protons are getting consumed per second, but since the number is so large, therefore they are able to 10 power 30 protons are able to cross this barrier, and we have the fusion reaction inside the core of the sun to give energy. Let's stop here. We shall start from this place. Thank you.